Hi, this is Dr. Chandran. Today's topic is plastic analysis. The following subtitles we are going to discuss in that topic: Introduction, Plastic Inch Concept, Plastic Section Modulus, Shape Factor, Collapse Mechanism, Theorem of Plastic Analysis, Static and Kinematic Theorems, Plastic Analysis of Beams and Photo Frames by Equilibrium Methods. So before entering into the topic, just recall the stress strain curve of a mild steel. We have four zones: linear range, yielding, then strain hardening, then necking. The point 0 to B, this range, this is called linear range. B to C, this range is called yielding. C to D, this is called strain hardening. Then D to E is called necking. Okay, four ranges, just to keep in mind. In the elastic analysis, the design load is nothing but yield load divided by factor of safety. What is yield load? This is the point. The load at which the yield stress develops, that is called yield load. This load divided by factor of safety, which gives design load in the elastic theory. But in the plastic theory, design load equal to ultimate load divided by load factor. What is ultimate load? The load at this point. The load at this point is called ultimate load. This load divided by load factor, which gives the design load for the elastic theory. Okay. The assumptions are in plastic theory. Plane section remain plane in plastic condition. Stress strain relation is identical both in compression and tension. Plane section remain plane, implying that the strain distribution is linear. Deformation is small. Process of yielding of a section. Consider a rectangular beam. It is subjected to moment M. The moment value is increasing gradually. At elastic limit, the moment is sigma into Z. So this Z is the section modulus, sigma is the stress, elastic stress. Okay, elastic limit stress. Okay. Then MY is the yield moment. This yield stress into section modulus. So the first diagram, the stress within the elastic limit. Second diagram, yield stress is maximum at the extreme fiber. In the third diagram, the yield stress is maximum at the extreme fiber at certain nearby extreme fibers also. In the last diagram, the fibers above the neutral axis fully subjected to yield stress, below the neutral axis also subjected to yield stress. This condition is called a fully plastic condition. In this condition, the moment is called plastic moment. Okay. Next, what is plastic hinge? When the section is completely yielded, the last diagram, the section is fully plastic. A fully plastic section behaves like a hinge. That is called a plastic hinge. That is nothing but plastic hinge is defined as an yielded zone due to bending in a structural member at which large rotation can occur at a section at constant plastic moment MP. Okay. Then there are two types of hinges: mechanical hinge or structural hinge. Right side, plastic hinge. In the mechanical hinge, the moment is zero, but in the plastic hinge, there is a constant moment MP. What is plastic moment? Plastic moment at which entire section is under yielding condition. Okay, C equal to T. The last diagram, please recall that last diagram. C equal to D. What is C? This is the compressive force, T is the tensile force. Area into stress. Area into stress. Okay. Each area, that is half of the area, is occupied by each zones. Okay. Neutral axis divide the cross sections into two equal parts. C equal to T equal to A by 2 into sigma Y. Now this is the diagram. Already we have seen that. Here, compressive force acting at the top portion, tensile force acting at the bottom portion. Okay. If you take moment at center for the two forces, so the center of gravity, center of the force C from the neutral axis YE, then the center of the tensile force from center equal to YT. So we can calculate the couple at center, that is the couple equal to sigma Y into ZB, where ZB is nothing but plastic section modulus. So ZB by Z always greater than 1. This is called shape factor. Okay. In other ways, we can say shape factor is nothing but plastic moment to elastic moment, also called shape factor. Now, how to find the shape factor for various sections. First, we have to consider a rectangular section. Section modulus is Z equal to I by Y. So this is called elastic modulus. P d equal by 12, then Y equal to extended by distance d by 2, that is equal to PD square by 6. Plastic modulus equal to ZB, A by 2 into YC, YT. We can have, so YC and YT is nothing but the centroid of the compressive force from this T by 4. T by 4, we can get the PD square by 4. So shape factor equal to ZB by 1.5. Like then we can calculate the shape factor of other sections, circular and triangular and I section. So if you see this triangular section, the shape factor equal to 2.346. Then I section is 1.132. Then circular section is 1.7. See, the purpose of finding the shape factor is you can find out this section modulus easily, because we know plastic section modulus, which is nothing but elastic section modulus into shape factor. Okay, load factor. Then load factor is nothing but collapse load divided by working load. Sigma Y into ZP by sigma into Z, the load factor. So load factor is the load at which the plastic is developed. So okay, collapse load equal to the load at which the plastic is developed, that is sigma Y into ZB. So working load is nothing but sigma into Z. Working load is nothing but sigma into Z. Sigma into Z. Okay, sigma is nothing but sigma Y. Here also we can say sigma Y. Working load. Okay, rectangular, for rectangular section, load factor equal to 2.25. For rectangular section, load factor equal to 2.25. Then factor of safety. Factor of safety is equal to yield load divided by working load. See, W Y by W, sigma Y by sigma, that is we can give 1.5. So elastic analysis we are using factor of safety, plastic analysis we are using load factor.